Okay, let's look at the results now. Owing to the interaction between the tipping elements and their respective critical temperatures are effectively shifted to lower values except for Greenland. For West Antarctica, okay, so now they refer to this figure here. Okay, see Greenland figures 4B and C. That's this panel and that panel. For West Antarctica and AMOC, we find a sharp decline for interaction strength up to 0.2 and an approximately constant critical temperature range afterwards. The effective critical temperature for the Amazon is only marginally reduced due to the interactions within the network, as it only influenced by AMOC via an unclear link. Okay, so panel A shows a shift of critical temperatures, right, due to interactions. Now, the scale here is in the degrees C, right? 1, 2, 3, 4, 5, 6. This is the same scale straight across. So this is also temperature changes here, or critical temperature, right? If you look here, right, all these spacing correspond straight across. So, you know, we see an increase of about 4 degrees C, etc. Gray bars indicate the standard deviation. Okay, these bars correspond to the critical temperature ranges in cases of zero interaction. Now, B and C, changes in critical temperature ranges with increasing interaction strength along the x-axis. For the Greenland ice sheet and West Antarctica ice sheet in B, West Antarctica is in purple, Greenland's in blue. And then the Atlantic AMOC and the rainforest in C. So here's the interaction between the two ice sheets and then between AMOC and the rainforest here. So what this is showing is that the critical temperature is increasing with respect to Greenland and moderately decreasing when looking at AMOC and the Amazon rainforest. So what's going on here? Okay. All other interactions, if you read the statement, effectively shifted to lower values. That's for all other interactions. In other words, the cumulative, the synergistic effect reduces the critical temperature where there is a transition in the state, except, according to this study, except for Greenland. They're basically saying that the interactions is a negative feedback loop, thereby increasing the temperature for which any transition in the state would result. So all the other interactions working together, the temperature decreases that would initiate a transition state. Except for Greenland, is that with Greenland, the critical temperature to initiate a transition state increases. That's according to them. I still wonder if they took into account the major oceanic heat content that's going on in, that the ocean contains, especially the upper 500 to 700 meters. I think, whether there's the intermediate water, surface water flowing, whatever, that heat is going to diffuse and basically have an effect. You still have currents moving, bringing in the water, the warmer water. So I am not sure if they took account of that. So I'm going to put a caveat on that result there. So they basically talk about, in particular, the ensemble average of critical temperature interaction strength is lowered by about 1.2 degrees C, about 40% for West Antarctica ice sheet, 2.75 for AMOC, and 0.5 C for the Amazon, respectively. This is due to predominantly positive links between these tipping elements. And I referenced figure 1 that I showed you earlier. In contrast, the critical temperature range for Greenland ice sheet tends to be raised due to the interactions with the other tipping element, accompanied by a significant increase in overall uncertainty. This can be explained by the strong negative feedback loop between Greenland and AMOC that is embedded in the assumed interaction network. On the one hand, enhanced meltwater influx into the North Atlantic might dampen AMOC, positive interaction link. On the other hand, a weakened overturning circulation would lead to a net cooling effect around Greenland. Thus, the state of Greenland strongly depends on the specific parameter values in critical threshold temperatures and interaction link strength of the respective members there. Overall, the interactions are more likely, this is the summary of the results. Overall, the interactions are more likely to lead to a destabilization within a network of climate tipping elements, with the exception of the Greenland ice sheets. But they kind of hinted at it here. It could be situations where the Greenland ice sheet will still destabilize, and all of it destabilizes. But no matter what, if you take this overall, there's a destabilization taking place that will lead to basically changing whatever the condition, the current state, into something different. As I've argued before, the system is so perturbed and continues to be perturbed that Earth is not going to be able to settle into its new equilibrium state. Think of chaos theory. You have constant perturbation that the system cannot find its new equilibrium situation. And that is what I think is happening on the planet now. We're already seeing the transitioning of the states here. Where it's going to lead us to? Stay tuned, right? Risk of emerging tipping cascades. Tipping cascades occur when two or more tipping elements transgress their critical thresholds for a given temperature level. We evaluate the associated risk as the share of ensemble simulations in which such tipping cascades are detected. For global warming up to 2 degrees C, tipping occurs in 61% of all simulations. This comprises the tipping of individual elements, as well as cascades including 2 elements, 3 elements, 4 elements. As the coupling between the tipping elements is highly uncertain, we introduce an upper limit to the maximum interaction strength and vary it from 0 to 1. The highest value of 1 implies that the interaction between the elements is as important as the non-linear threshold behavior of an individual element. For lower values, the interaction plays a less dominant role. Basically, a value of 1, that's the highest, that's the most dominant situation, where the most interaction will take place. Tipping cascades are first induced as warming levels around 1 C above pre-industrial, where the lower bound of the critical temperature range for the Greenland ice sheet is exceeded. The bulk of tipping cascades, however, is found between a 1 and 3 degrees global mean temperature increase. This is true for all cascade sizes. For temperatures above 3 C, increasing global mean temperature, cascades occur less frequently as most of the tipping elements already transgressed. So basically it already happened at 1 to 3, so 3 to 5 or greater, it's already took place. We find that in up to 65% of all ensemble simulations, the Greenland ice sheet triggers tipping cascades. At the same time, it occurs as frequently in cascades as the other tipping elements. Thus, we call Greenland a dominant initiator of cascades. I think Greenland is the important initiator. I find that interesting. I can understand why they would say it's a dominant. I want to know what they think about the Antarctic ice sheet. So let's go on. Following this argument for Greenland, the West Antarctic ice sheet is both an initiator and mediator of cascades, as it occurs often in cascades and likewise often acts as the initiator. So basically, it can initiate or it could be on the receiving end. Basically, is what they're saying. Although the frequency of occurrence in cascades is very similar for AMOC as for the two large ice sheet, it is a dominant mediator of cascades, as it does not initiate many cascades. Lastly, the Amazon rainforest is a pure follower in cascades because it's only influenced directly by AMOC and cannot influence any other tipping element itself. The reason why the ice sheets often act as initiators of tipping cascades in a model is likely because their critical threshold ranges tend to be lower than for the other tipping elements. Many cascades are then passed on to other tipping elements, especially AMOC. Thus, the role of AMOC as the main mediator of cascades can be understood from a topological point of view, as the AMOC is the most central network element with many connections to the other tipping elements, right? Directly connected to the Greenland ice sheet, the Amazon, Antarctic ice sheet, so forth. As such, AMOC connects to the two hemispheres, north and south, and can be influenced by both Greenland and West Antarctic ice sheet. Okay. Now they finally bring in ENSO, because ENSO really is quite important in the climate situation and the climate effects. While many tipping elements, including ice sheets, AMOC, Amazon rainforest, to a first approximation exhibit a transition between two or more alternative stable states, often described by the paradigmatic double-fold bifurcation. I discussed bifurcation briefly in my ocean tipping point video. Tipping of ENSO could rather imply a transition from irregular oscillatory occurrences to a more permanent state of strong El Nino conditions. And you heard me say that before. I mentioned that earlier, what's going on here with ENSO. I mentioned ENSO in the ocean tipping point video, as I have in previous videos, and I did a whole deep dive on ENSO itself, that indications are that ENSO could lead to an El Nino permanence, that the El Nino condition of the ENSO cycle predominates. That seems to be, studies are indicating that. A more frequent occurrence of El Nino events could have strong impacts on global ecosystems, up to a potential dieback of the Amazon rainforest. While some studies have emphasized the uncertainty about future ENSO changes, another study found that the frequency of El Nino events could increase twofold in climate change scenarios and simulations of the CMIP3 and CMIP5 models, as well as in perturbed physical experiments. Also, some ENSO characteristics appear to respond robustly to global warming. That is, dramatic changes, such as an intensification of ENSO-driven drying in the Western Pacific, and rainfall increases in the central and eastern equatorial Pacific due to nonlinear responses to surface warming. Moreover, from an observational point of view, it was found that the global warming trend since early 1990s has enhanced the Atlantic capacitor effect, which might lead to more favorable conditions for major El Nino events on a biennial rhythm. It's another way of saying tropical waters are getting warmer. And El Nino events are characterized by a warm Eastern Pacific. So that Atlantic capacitor effect, because of teleconnections, will move over to the Pacific side. Paleoclimate evidence from Pliocene, 5.3 to 2.6 million years before present, with atmospheric CO2 levels comparable to today's conditions, suggests that there may have been permanent El Nino conditions during that epoch. However, it must be noted that the Pliocene is different in terms of the continental configuration compared with today. Basically, sea levels, that's what they're referring to. Given the particular uncertainties regarding ENSO compared to the other tipping elements considered in our analysis, we excluded it and its interactions with the other tipping elements from the main analysis above. I was wondering about that. However, we performed a comprehensive structural robustness and sensitivity analysis, including ENSO as a tipping element. For this purpose, we choose to represent ENSO in the same way as the other tipping elements. A typical transition time of 300 years is chosen. The critical temperature threshold lies between 3.5 and 7 degrees C above pre-industrial levels. That's basically to affect And so, and our analysis is based on simulations of 11 million ensemble members arising from the 27 different network combinations from the links and so on. This is where you need high computing power. Our robustness analysis reveals that the roles of the tipping elements remain qualitatively the same. The ice sheets remain strong initiators of tipping cascades. AMOC remains a mediator, and the rainforest pretty much tags along. Okay, discussions and conclusions, right? A little bit here, and then, this will wrap up our discussion here. It has been shown previously that the four integral components of the Earth's climate system, mainly considered here, are at risk of transgressing into undesirable states when critical thresholds are crossed. Over the past decade, significant changes have been observed by the polar ice sheets as well as the AMOC overturning in Amazon rainforest. Should these climate tipping elements eventually cross their respective critical temperature thresholds, this may affect the stability of the entire climate system. Entire climate system. In this study, we show that this risk increases significantly when considering interactions between these climate tipping elements, that these interactions tend to have an overall destabilizing effect. Altogether, with the exception of the Greenland ice sheet, interactions effectively push the critical threshold temperatures to lower warming levels, thereby reducing the overall stability of the climate system. The domino-like interactions also foster cascading, nonlinear responses. By the way, the nonlinear, that's basically exponentiation. That's what they're getting at. Under these circumstances, our models indicate that the cascades are predominantly initiated by the polar ice sheets, and the AMOC is a mediator. Therefore, our results also imply that the negative feedback loop between Greenland and AMOC might not be able to stabilize the climate system as a whole. There we go. Now, that might be, without them referencing it, that might be an acknowledgement of the ocean heat content and how much energy is in it. And as I said, when I first started this channel several years ago, I talked about how, shutting down AMOC or slowing it down will lead to a cooler condition. That's kind of, so basically it will stop the melting of Greenland and then and stabilize it. I discussed that. But now with all that extra ocean heat in the water and it's not being sequestered, that's going to change that. And this is a very important statement. Okay? Right there. Our results imply that the negative feedback loop connecting Greenland and AMOC might not be able to stabilize the climate system as a whole. Now, could there be a slight negative feedback loop? Perhaps. But with the increasing warming air temperature, and don't forget, we're losing the sea ice there, so the Arctic is going to warm up because we don't have the albedo now. So, yes, Greenland ice sheet will have some albedo, but you got the rest of the Arctic Ocean there. So you're going to have warmer temperatures continuing to melt the Greenland ice sheet. So still going to put the fresh water in there, whether or not AMOC is slowing down, plus the ocean heat content is going to continue with the warming. So I'm glad to see that statement there. What they're basically saying is that overall, everything taken overall, destabilization of the climate system is currently underway, and to really change the really transition to another state altogether, with the interactions of all of these factors that they looked at, the temperature is a lower temperature is required to initiate that. So think of additive effects. While a conceptual model evidently does not represent the full complexity of the climate system, is not intended to simulate the multitude of biogeophysical processes or to make predictions of any kind, it allows us to systematically assess the qualitative role of known interactions of some of the most critical components of the climate system. The large-scale Monte Carlo approach further enables us to systematically take into account propagate the substantial uncertainties. Overall, this work could form the basis of more detailed investigation using more process-detailed Earth system model that can better represent the full dynamics of each tipping element interactions. And they go on to say, in the future, complex climate models might be driven with advanced blah, blah, blah. So let's see, what do they say here? Some examples of relevant processes that could be investigated are the following. Changing precipitation patterns over Amazonia due to a tipped AMOC. Whether rainfall patterns will increase or decrease. Whether this will be sufficient to induce a tipping cascade. This would shed more light on the AMOC-Amazon interaction. Second, the influence of disintegration of the West Antarctic ice sheet on AMOC could be further studied by introducing freshwater input into the Southern Ocean. Similar to, just like what I discussed earlier in all that freshwater input into the Arctic Ocean. Some studies suggest that freshwater input into the Southern Ocean at a modest rate would not impact AMOC as much as freshwater input into the North Atlantic. Well, it's closer, right? While higher melt rates could have more severe impact on AMOC. With carefully calibrated coupled ice-ocean models, including dynamic ice sheets, ice-ocean tipping cascades could be studied in better detail. Further, the timescales for potential tipping dynamics need to be more rigorously explored in contrast to the conceptual approach used here. So what they're doing here, they're basically admitting some of the shortcomings, and that's fine. It's a starting point. They're trying to do a model of all these elements put together. So kudos to the researchers for undertaking this task. It's an important task. I mean, a lot of the other models we've looked at, and I've discussed with you, it's like, okay, ice melt does this. What happens then? Temperatures, CO2 is doing this. What happens to temperatures? What happens, direct. But now they're looking at, we've got the ice melting here. We've got the AMOC here. What happens when they work together? What's the effect there? So this is an important start. Yeah, the admitting some of the perhaps deficiencies, that's fine. Any good objective scientist will do that with their research. It is important to note that the transition of one tipping element has a delayed effect on the other elements, especially in the case of the slowly evolving ice sheets. Their temperature threshold is lower than for the other tipping elements because, it doesn't take much to melt it. 1 degree C, it will melt ice, right? The disintegration would unfold over the course of centuries up to millennia. Therefore, meltwater influx into the ocean and changes in sea level would affect the state of the other tipping elements only after a significant amount of time. Therefore, our analysis of emerging tipping cascades needs to be understood in terms of committed impacts over long timescales due to anthropogenic interference with the climate system. Finally, it appears worthwhile to perform an updated expert elicitation along the lines of Kriegler et al. In 2009, where additional interactions, tipping elements, and a better understanding of the interaction strength would help us narrow down the space of possible scenarios and uncertainties that have been investigated here. So in other words, as we improve our methodologies, our modeling improves, we get better data, more comprehensive data, we can improve what they're doing here. So to sum this up, I've been saying this kind of in places in this video. A lot of models look at they identify, Greenland, Antarctica, AMOC, Amazon, and so, right? A lot of models look at what happens as these things changes. What's affecting those? Increasing air temperature, was that due to the Greenland ice? Okay, sea levels go up, we're melting, we're losing the Arctic sea ice, what does that do for temperature? They look at the individual aspects and model that. Here they try to undertake modeling of, because Earth is a complex system, of some of the interactions. So what happens when these start working together? This one and this one, this one and that one, and so forth. So they started to look at these possible interactions and what does that do? And what they basically found is that the temperature that would initiate a change in the state, in other words, from the current state to something different, is actually lowered when there's an interaction. Think of, like, in statistics, you have two independent variables. Okay, what does variable A contribute? What does variable B contribute? What's the interaction of the two variables contributing to the response? So this is a first step. You have to start somewhere, and so they're trying to do this, and I give them credit and I give them chops for undertaking the study here. And as they pointed out, there's some areas for improvement, and I pointed out my my little quibble, if you can call it that, or caveat, however you want to characterize it, about the ocean heat content. I think that the ocean heat content basically mitigates, if not negates, any negative feedback loop between AMOC and Greenland, or it definitely reduces it at the very least, if not, as I just said, negate it. So what they're saying here is that overall, these interactions are lowering the threshold that will basically lead to an unstable climate interregnum, if you will. We're going from one climate state to another, and that transition is going to be very unstable. That's the perturbation. Where does it settle in on? Who knows, if it ever does, because the perturbations continue. So what they're saying is the exponentiation, the interactions of these major factors will lower the temperature that destabilizes Earth's climate system. Think about that. That's the take-home message here. A lower temperature is required to completely destabilize the climate system. We have an abrupt change, and you're in a transition state to what? Who the hell knows? One other thing I wanted to point out to you. It shows you how long it takes to get these things published. I speak from firsthand experience. Received in March 2020. Discussion started. That means the referees give their input. We think you should do this. We think you should do that. Remove this. We'd like to see something added addressing this issue, what have you. So they send that in. Then it's revised. Okay, so they do the discussion. It's initiated in 2020, in April 2020. So somewhere between April 2020 to March 2021, there is the discussion and the revision takes place. So basically, an 11-month period. So they resubmit it a year later, in essence, and then it gets accepted, and then it gets published. So from first submittal to final publication, we're talking about 15 months. This is typical. And by the way, some of these folks here, look at where they come from. Potsdam Institute for Climate Impact Research, PIK. Okay, that's in Potsdam, Germany. This is a research institute of extremely high repute, excellent reputation, and they do a lot of climate research. So you got some heavy hitters, Potsdam, Germany, Berlin, Germany, Stockholm, okay, and then a gentleman from Novgorod, Russia, which means new town. Seriously, Novgorod means new town. But yeah, so we have this. Unfortunately, the Europeans are now taking the lead on climate studies. Unfortunately for American scientists, because of funding issues. But hey, the work has to be done, and these guys do good. They do good work over there. So anyway, I know it's kind of wonky and convoluted, but there you have it. Interactions are going to lower threshold temperatures that will cause climate instability, and the state of the climate will become unstable at lower temperatures. That's what they're saying. So until next time, thank you for your time. Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.